Testing. Okay, so it's 7:30. So please return to your seat and we will start the lecture shortly. Okay. So yeah, so last week we've discussed about the so-called rotation order problem. So even for the same rotation in Euler space, so for example, 40, 50, and 0, okay, it will, based on the different ordering of the rotation, we may generate different results, okay? So this is a very big issue in some cases, okay? Especially if you are very familiar with Blender, for example, okay? So there are lots of different built-in ordering rotations, rotation orders, okay? So you can select one. But the problem is that when you, for example, you can imagine when you generate these models and import into Unity, there might be some problems, okay? And also if you generate, for example, you made an animation in Blender and you import into Unity, and this particular animation may involve some rotations, then you may be in trouble, okay? So these are the problems with rotation. And to solve one of the most prominent problem with rotation, the gimbal lock problem, we have to use quaternion. Okay, so quaternion is something that may be a little bit unfamiliar for some of you, okay? But in general, it is very easy to understand, okay? So as you may have already known that in Unity, we have the, it's not a vector 4, but it's very similar. Okay, so we have these x, y, z, and w. Okay, so if we use this as entire 4x1 matrix, basically, or vector, okay, we have the quaternion. Okay, so in Blender, it is w, x, and z. Okay, so the order is slightly different. So that's why sometimes when you import a particular model into Unity from Blender, and you will get some errors and unexpected rotations, okay? Yeah, in many 3D engines, quaternions are always normalized, okay? So this is also very important. So for example, in Unity, quaternion is always normalized, okay? So even, you, of course, you can assign a number. So for example, 4, 4, 4, 1, for example, okay, for X, Y, Z, and W respectively, okay? You can, of course, do so. But when we talk about the rotation, Unity will always do the normalization first and then apply this rotation. Okay, so even you do this it will not actually work. Okay, so in Unity, you can you have a function cotangent dot Euler to convert Euler angles to cotangent. Okay, so I guess many of you have already know this. Okay, so I will not repeat that. And also cotangent has the property Euler angles for you to convert rotation from cotangent to Euler angles. Okay, so very straightforward. Okay, so before I introduce 3D rotation, I just want to use 2D rotation as an example. Okay, so I guess this is very familiar to you. Okay, so if we represent, for example, a point on this 2D plane. Okay, let me grab my pen. Okay, so this is the point we want to represent. Okay, on this 2D plane. Okay, we can always use x and y, right? So this is very straightforward. But this 2D plane is a little bit tricky. Okay, why I say so? Because this 2D plane has an imaginary axis. Okay, so it's not the typical x and y plane. Okay, so so this point is 0, 6, I. Okay, it's not 0, 6. Okay, so this is very straightforward, right? So in this case, if we are talking about 2D rotation, you can simply apply this formula and you will get the rotation. Okay, so you will get this one, okay, by simply apply this rotation. Sorry, this formula. Okay, so D is the degree that you want to rotate. Okay, so this rotation happens on 2D plane. Okay, so in general, you are basically rotating along this axis, but this axis does not exist, right? So it is the third axis. You can treat it as a Z. Okay, but anyway, so this axis is perpendicular to the XY plane, or the real and the imaginary plane. Okay, very straightforward, right? So this D is also very straightforward. We have this D in degree here, okay, and also this D here, okay. The only thing we need to do, let me check why it's not working. I don't know. Okay, so the only thing we need to do is to follow this formula. Okay, so as you can see, this dot, this xy can be represented because it's on the real and the imaginary plane. It can be represented as xyi, right? So very straightforward, right? So we put x plus yi here, okay? And this is about the rotation, okay? So this is a rotation. This is something that you have to memorize, okay? You have to memorize, but it's very straightforward. Cosine d plus sine d times I, okay? And then we just do this calculation and we can, do this, and then we will get something. You try to do some, manipulation of the formula, and you want to get something that is something real plus something imaginary. Okay, so you just massage the formula a little bit and you get this, okay? And then this part will become the new x and this part will become the new y, okay? So it's not magic, okay? You can actually do this, okay? If you want to turn this into this, the only thing you need to do is I times I equals to -1. Okay, so just in case you do not know complex numbers, okay? You only need to know this and then you can do the calculation. Okay, and you can check whether this formula is the same as this one. Okay, they are the same. Okay, so that's how we do rotations in 2D. Okay, but why I spend some time to talk about this? Because you can do the exact same thing in 3D. Okay, so this is the example. I will just skip that. Okay, so you can try to do some simple calculations. Yeah, as I mentioned, the 3D rotation can be exactly the same as the 2D rotation. Okay, so but in this case, it's a little bit, I would say, trickier. Okay, why I say so? Because in 3D, as you can imagine, you can rotate along any axis. It doesn't need to be Y or Z axis. Okay, so for example, if you want to rotate this X, Y, Z along this particular axis, so this axis can be represented as ABC. Okay, so ABC is a point, of course, right? But when we talk about vectors represented as ABC, then basically it simply means from the origin to the point ABC. Then that is the vector. and also the direction, right? So this is the axis we want to rotate. So if you want to rotate X, Y, Z along ABC, you can do it like this, okay? So first of all, you convert this point into this format. Okay, so this is the same as the previous one. Okay, so for example, this is 4, 1, right? You just make it 4 plus 1i, right? But in this case, this is 3D, right? So we have ij and k, right? So it can be represented as xi plus yj plus zk. Okay, so this is how we represent this point. Then how about the rotation axis? Okay, so the rotation axis is AI plus BJ plus CK. Okay, so this is the same format, right? How you represent ABC as a point in 3D space, right? So in general, I think XI plus YJ plus ZK is the same as AI plus BJ plus CK. They are the same, right? So they share the same format. But for the rotation axis, you need to be careful. Okay, you need to be careful. You need to make sure that this rotation axis is normalized. Okay, before you do the calculation, it must be normalized. So what do I mean by saying normalization? Okay, so if you have the square of A plus the square of B and the square of C equals to 1, and basically in general, this vector ABC is normalized. Okay, so very straightforward, right? I guess many of you know this because this is just secondary school math, right? Then you can do the cotangent thing here. Okay, this is the magic again. Okay, this is the magic again. You look at this. Let me go back to here. So you have cosine D plus sine D times I, right? So I is the imaginary axis, right? So we can do the exact the same thing. We have cosine D. I will talk about why we have D divided by 2, okay, later on. But we have cosine D here, right? You see sine D here, right? But this time is not rotation along the axis that you cannot see, right? This time we rotate these dot along this axis. So we have AI plus BJ plus CK. So that's it. We have cotangent. Okay, so it's very straightforward. Okay, how you can convert this into this format? Okay, X, Y, Z, W format. Okay, this is also very straightforward. Okay, you remember when we have this one, okay, we want something imaginary and something something real followed by something imaginary, right? So this is the same thing. We want to massage this formula a little bit, okay, and get what? Get something real plus something imaginary plus something imaginary J plus something imaginary K, right? And then we just have the coefficient. Then the coefficient can be WXYZ, okay? So that's it. So W is the real one, okay? I is the coefficient, X is the coefficient for I, okay? Y is the coefficient for J, and Z is the coefficient for K, okay? Then that's it, okay? So very straightforward. So yeah, so back to the topic, why we want to divide D by 2, okay? The most straightforward and also the simplest answer is that when we do the rotation of P, we have to use Q times P and then times the Q to minus 1, okay? This is basically the transverse of Q, okay? So why we want to do this? Because otherwise you will have basically D times D, right? So now we have D divided by 2 first, okay? So that we will not overshoot the rotation, okay? So this is the simplest answer. The longer answer is that if you do this calculation, you will learn why, okay? Yeah, when you do this Q times P times Q, and you will find that a lot of the calculations can actually be canceled out. Okay, so that's why we have to have D over 2. Okay, D divided by 2. Okay, so So yeah, so this is what I said. So if you want to find the quaternion, find something real, find something related to I, find something related to J, and find something related to K. And you have W, X, Y, Z like this. Okay, so very simple, right? Okay, so any questions about the quaternion? Okay, so yeah, I guess the calculations are very simple, but I will just ask you one simple question. Why don't we use this quaternion in, for example, unity to represent the rotation of an object? Okay, at the behind the scene, we always use quaternion to do these, game engine programming, things like that. Okay, and later on, I think you will have a core course, right, on game engine. Okay, you will learn this. Okay, but my question would always be, more like human-computer interaction. Why don't we use this directly in the interface of Unity to let you manipulate an object using this quaternion? Why? No gimbal lock? Yeah. This is the good thing about quaternion, right? But why we don't use it directly in Unity? I mean, the interface of Unity, right? So on the interface, you have something like, sorry, I have to, yeah, okay. So in Unity, if you select an object, you will see a menu like this, right? So this is the inspector, right? So in the inspector, you have a pose, position, and rotation, right? And then you have X, Y, and Z. And this one is also X, Y, and Z, right? I guess by now, you should be very familiar with this interface, right? But for the rotation, as this gentleman said, a quaternion is very good. It can avoid gimbal lock. But why don't we just add a W here and then make this, rotation, the quaternion of the rotation directly, visible to the user? Yeah. Many people do not know what W is, right? Yeah. Actually, for most of the user, we don't know W, X, Y, and Z. Okay, so it's actually very difficult. So you can actually do a very simple programming. Okay, so for example, you can program, for maybe you do a text entry, okay, to directly enter X, directly enter Y, directly enter Z, and also directly enter W, and then convert it into a quaternion. This is very straightforward, right? So it's just a new quaternion, and based on the four text entries, right? And you apply this rotation to an object and have a look, okay? And you will find that it is very difficult for us to directly interpret a quaternion, okay, compared to something like the Euler rotation, okay? So that's the problem with quaternion. So any other questions? Okay. Yeah, this is not very easy to use. Okay, so yeah, so the next one would be besides how we position the objects, besides how we rotate the object, we also need to know a very important concept, that is a local versus global. Okay, so during the tutorial, one group actually asked a very good question. Okay, so if someone else want to move the player inside the VR world, okay, how I should implement that. Okay, so this is actually the answer. Okay, you need to create a parent for the controller, okay, controlled by a VR. Okay, why it is like so? Okay, so first of all, remember, in this hierarchy window, we have a very complex hierarchy once you have a lot of models, right? So remember, each one, okay, so you click on each of them, okay, you will see the position and rotation in the inspector, right? So remember, these values are local values, are always local values. Okay, so rotation is a little bit complicated because you have to do the multiplications between each quaternion, and then you have the answer, the actual global value. Okay, but I just use a very simple example. Okay, so let me just use a 2D example. Okay, so you can directly use it to 3D. Okay, so this is of course the origin, right? So we have 0, 0 as an origin, right? So then we have this point. Okay, so this is the point. Okay, so this point is 1, 1. Okay, so and then we just maybe let me erase this a little bit. Okay, so now we have a square like this. Okay, we have a square like this. This square is 1 by 1. Okay, very straightforward, right? So you can imagine this point is 2, 2. Right, very straightforward, right? So this point is 1.5 and 1.5, right? Everyone knows, right? Okay, so now I just tell you that this dot, okay, this dot is the child of the square. Okay, the child of the square, right? So it's the center, actually the center of the square. Okay, so now I do a very simple thing. I just move this square to the right. Okay, to the right. By what? By just 1 unit. Okay, so now this is the new location of the square, right? So you can imagine this central point of the square will also be moved to this point, right? So now what is the coordinate of this new dot? Okay, so maybe this is the new dot. Okay, so what is this? The coordinate. So it was 1.5, 1.5, right? So now what are the values? I moved it right by just 1 unit. Yeah. 2.5, 1.5, right? So very straightforward. Okay. Very easy to calculate, right? Okay, so the next question would be, if you click, okay, so imagine that the square and also the dot are 2 game objects in Unity. Okay, so and also we set up it like the dot is a child of the square. Okay, you click on this dot, what you are going to see in the inspector panel? What are the positions of these 2 game objects? Right, 0, 0, right? Okay, so I think this is the most straightforward answer, 0, 0, because there is no relative motion between these 2 game objects, right? So in this case, 0, 0 is the local position, right? And 2.5 and 1.5 is the global location of this dot, right? So that's it. That's the difference between local and global. Okay, so you can imagine that in many cases, if you want to move something in the virtual space, okay, you tend to move the parent instead of the child. Okay, otherwise you will create a lot of confusions, right? So if the child is not at 0, 0, 0, 0, okay, you may have a lot of trouble. Okay, so that's about local and global world coordinate space. Okay, so any questions? Okay, very straightforward, right? Okay. Okay, next we are going to talk about visual rendering. Okay, so visual rendering is very important because we have already talked about how we represent objects in the scene. But how these objects should look like depends on your visual rendering algorithm. Okay, so this will include something like view transformations, lighting and shading, surface normal UV mapping, and also global illumination, light maps, light probes, things like that. Okay, so let me go through it one by one. And some of the information have already been covered in my tutorial. Okay, so for example, when I talk about the scene building, I think I have already talked about something related to global illumination, okay, and also light probes. So if you want to see all this in action, okay, in Unity, you go to watch the tutorial videos. Okay, so view transformation is very straightforward. So we have to understand 3 basic view transformations. One is perspective. Okay, so this is how you use a Blender, how you use Unity by default. Okay, so in general, I think every 3D modeling tool will have this perspective as the default viewing projection or view transformation. Okay. The second is orthographic. Okay, so this is also very important, especially in some 3D modeling software for mechanical components. Okay, so in this case, as you can see, all the parallel lines, okay, of the 3D object will keep parallel. Okay, so this is the feature of orthographical projection or transformation. Okay, isometric is a very special form of orthographical transformation or viewpoint. Okay, why it is like so? Because it always requires that this line and also this line should have a 30-degree, okay, 30-degree angle with the horizontal line. So this is a very special case of orthographical transformation. Okay, so you can actually go to the isometric form in Unity as well. You just click somewhere. Okay, I cannot, open Unity on this machine because it's too slow. Okay, you have your view scene. Okay, you will see some gizmo here, right, on the top right corner, right. So there is one very tiny text below the gizmo. Okay, it by default it writes PERP, okay, which stands for perspective. Okay, you click on it, it will become ISO. Okay, ISO stands for isometric. Okay, so you are just changing the perspective from a perspective normal view transformation to this isometric view transformation. Okay, so this is how it looks like in Unity. Okay, so why we need this in some of the 3D software? Okay, so as I mentioned, in some mechanical modeling or the modeling tools for mechanical components, we need these isometric view transformations quite a lot. Okay, why it is like so? Because if you have ever tried to place something, okay, it's two 3D objects, you want to place something on top of another game object in Unity, okay, you will find it is actually very difficult to do. Okay, so why it is like so? Simply because of the perspective, okay, and also the manipulation. Because when you manipulate the objects, you always manipulate on a 2D plane. And this 2D plane is very hard to control. Why it is like so? Because it is always a projected plane of the entire 3D scene. Okay, so I think I explained this when we were in the cave. Okay, so for the frustum, because it's pyramid-like shape. Okay, so the further you look at, the more information you should be able to see, right? So that's why in these 3D windows, when you want to manipulate something, okay, you move a little bit to the z-axis, and you will find that it's off by quite a lot. Okay, in some cases, that's simply because this perspective transformation. But if you can always follow the isometric form, then it will be much easier for you to manipulate. Okay, so for example, if I want to place something on top of another thing, okay, I will always first change to isometric form, view transformation first, okay, and then I click on one of the axes. Okay, still remember this gizmo. Okay, I click on one of it, so I can have either a side view or a top view or a front view, right? And I do the manipulation along one particular axis first. Okay, and then I click again to go back to this 3D rendering form, and then I click on the other axis I want to manipulate. Okay, and so that I can do the manipulation very precisely. Okay, so this is why a lot of 3D software will have these three types of view transformations. And in VR, okay, we are always dealing with a customized projection. Okay, this may seem not that obvious when you do, for example, 2D game programming. Okay, because as I mentioned, we always suppose that the viewer will always look at the screen from the center, okay, at a fixed distance. Okay, Why we have such kind of assumption? Simply because ordinary monitors cannot check overhead, right? So still remember when we were in the cave, I used the marker, okay? When the marker is very close to one of the projection wall, okay, you will see a lot of things, just like you are seeing through a magic window, okay? Still remember that, okay? So you can imagine for an ordinary 2D monitor, on paper, it can have the same effect, exact same effect, right? The only thing we need to do is to track user's head, right? Okay, so but for an ordinary monitor, of course, we cannot track user's head, so we always make the assumption that people will look at the screen from the center at a fixed distance. Okay, so that's why the default projection matrix or the projection frustum will be symmetric. Okay, will always be symmetric. Okay. However, when we do the rendering to two different cameras, okay, the left eye camera and the right eye camera, we are no longer looking at the screen from the right center, right? So for example, in this case, the left eye and the right eye has a distance, okay? And this distance is called interpupillary distance, okay? The distance between your two eyes, you can basically treat it like this, okay? The pupils, okay? So in this case, as you can see, just like I mentioned previously, this the left eye camera has an asymmetric frustum like this. Okay, so the right eye also has an asymmetric frustum or off-axis frustum. Okay, so there are more cases. Okay, so for example, this is the case that we discussed in the cave, right? So we move to the left, to the right, sometimes more closer to the screen, right? So in every case, you can imagine there is a very, very tiny little chance that the viewer stands right in front of the screen, right? So in many cases, this rendering frustum is asymmetric, is off-axis. Okay, so another way to simulate this is to use a toe-in approximation. Okay, so this approximation will actually create some artifacts. Okay, so I will not dive this into the very detail, but you can imagine that if we just turn this camera a little bit to the center, okay, we also can have these effects without having these off-axis frustum, right? So in this case, this frustum, this one, and also this one, okay, they are still symmetric, right? They are still symmetric, but the problem occurs at the right and also left and the right edges of the screen. Okay, so you can imagine if we use this and then develop the cave, then we will have some trouble at the joints of the cave. Okay, because these this is just an approximation, right? So for any approximation, we have the arrow, and the arrow can be quite large at the edge. Okay, the edge is where the two cave screens will meet together, right? So this arrow will be actually magnified. Okay, so in some cases, if I draw a cave like this, okay, so this is the front screen, this is the right screen like this, okay? So you will see a line rendered like this. Okay, this is simply because that they used the toe-in approximatics.